Well, good afternoon, everyone. I just can't tell you how happy I am to be here to help celebrate the 10th anniversary of MANA. I thank the organizers of MANA and my friend Sasaki-san for inviting me. I'm pleased to tell you about the bulk photovoltaic effect in polar oxides, and I think you will see that there are interesting materials architecture issues that greatly affect this physical property. Okay, I think people are familiar with photovoltaics in general. You have a semiconducting material, so you have valence band edge, conduction band edge. If you use light with photons that are too big, then you have some excess energy as the carrier descends to the band edge. If you use photons with energy that is too small, then the light is not absorbed. These are two sources of reduced efficiency in photovoltaics. In conventional photovoltaics, you make a PN junction or some other interface between two materials, and you can have a limit to the efficiency of such devices that is referred to as the Shockley-Queisser limit based on detailed balance and the two types of energy loss that I mentioned to you. And so for any particular band gap of material, there is a maximum efficiency. So the efficiency is never higher than 30% or so, but in fact for high band gap materials, the efficiency is quite a bit smaller. Okay, but there are other photovoltaic effects that are not the same as the conventional one that you may be familiar with, and this was discovered by Vladimir Friedkin and his co-workers. This, when it says 567 material, this is like antimony sulfide iodide from columns 567 of the periodic table. And so you can see a current for different frequencies of light. I will tell you how this bulk photovoltaic effect is different, but the main way is a single material exhibits this photovoltaic effect. You do not need an interface between two materials. And this was found in other materials. This is a very early famous experiment relating to lithium niobate performed by Alistair Glass at Bell Laboratories and his co-workers just a few years after this initial report. Okay, so what you can see here, this is an experiment for varying light intensities. Here you get the current versus an applied voltage. And what you see here is that no matter what intensity you have, the same voltage or the same applied electric field takes away the current. And so you have the same open circuit voltage for different intensities. That is a signature of this bulk photovoltaic effect. And you can find photovoltages that greatly exceed the band gap. So that's a very appealing feature of this phenomenon. Okay, so recently there has been a renaissance of interest in bulk photovoltaic effects, and one material that has been widely used is bismuth ferrite. And so this paper is by the group that is led by Ramesh, who is now at Berkeley. And so this is an exploration of bulk photovoltaic effect in bismuth ferrite film. Yeah. Don't be too short. I shall persevere. Just a typical day in Japan, right? Okay. So the idea of this slide is that if you have a material with ferroelectric domain walls, you can find very large photovoltage. And the hypothesis put out by these authors is that the domain walls each act as p-n junction. And so in a sense, this is like a tandem solar cell exhibiting strong photovoltage. But some other authors, led by Marin Alexei, have shown that it is not only domain walls that provide photovoltaic effect in ferroelectrics. Okay, so this experiment, can you see here, this is a series of domain walls with the material polarized up and down and up and down. But if you put the electrodes this way, then you are collecting current across the domain walls. But if you put the pads this way, you're collecting currents parallel to the domain walls. So you're not using the domain walls to enhance the photocurrent or the photovoltage. And so this is a very interesting experiment. What they find on the left is that this geometry, of course, gives photocurrent and photovoltage. And at high temperature, the other one does not. But at low temperature, both of them give photocurrent and photovoltage. So if you can take away the conductivity of the domain walls, then you can get photocurrent either way, showing that this material has a bulk photovoltaic effect. Okay, so this is again sort of a cartoon image of what we think is happening. You have valence band and conduction band. You excite carriers. And in general, these carriers would go in either direction in a single material. But if you have a material that breaks inversion symmetry, this separates left and right, up and down, and so the carriers have a preferred direction. So that's illustrated by this line here. The carriers move preferentially in one direction. They, of course, start to lose energy, but they move a considerable distance as hot carriers. So this is truly a quantum mechanical effect. This is not just a quasi-classical effect. Okay, and so this is a recent result by my friend and collaborator Jonathan Spanier with Vladimir Friedkin, again showing current versus electric field as linear, and all of them cross zero at the same. So as you vary the light intensity, you get the same photovoltaic field and voltage. Okay, so this leads to the hypothesis that the current is traveling for only a finite distance as a hot carrier, as I showed you on the previous slide. Okay, so a particularly exciting development happened in the last few years, and that is the idea of collecting these bulk photovoltaic currents at the nanoscale. And this is where the architectonics aspect starts to play a role. So this is another paper by Marin Alexei, and he showed two geometries. You can see the cartoon here. One where you have a material with conventional electrodes being used, and then the same material where one of the electrodes is a tip. And what you see is that you get similar amount of photocurrent, but the tip is only collecting from a very small area, whereas these electrodes are collecting from the whole region. So what is the origin of the enhancement of this tip? So this is the geometry that we're talking about, shown in a larger scale. You take a ferroelectric material that is non-centrosymmetric, breaks inversion symmetry, so it has a preferred direction. But then you collect the current with a sharp tip. This is like an atomic force microscope tip, and you use either laser light or AM 1.5 simulated sunlight and report the current and voltage. And so here are the results from the experiments in Philadelphia. You have the current as a function of time. You turn the light on, you get a spike of additional current at the beginning. This is thought to be a pyroelectric effect, but then you get a steady state current as long as you wait until you turn the light off. And so here you can see the ferroelectric material has a photovoltaic current. You get a strong current even at zero voltage, whereas in a control sample, this is strontium titanate, you get no current when you apply no voltage. This is a conventional sweeping of photocurrent, and this is an actual photovoltaic effect. Okay. So the experimentalists ran this experiment with the sharp tip with a 25 nanometer radius, but also with a much more blunt tip with a 5 micron radius, and the photocurrent is just about the same. So this shows you that the tip radius is not the relevant collection radius that sets where the current is coming from. And so again, we are saying that it is really a quantum hot carrier effect, and the thermalization radius for these hot carriers sets the region over which the experiment is collecting current. Okay, so one thing that I would draw your attention to is that the external quantum efficiency, this means the number of electrons per photon can be greater than 1. And so this experiment, this is the bulk photovoltaic effect with the nanoscale tip, is observing impact ionization or other effects such that one photo-generated carrier leads to more than one electrically detected carrier. Okay, I sort of already mentioned this. Okay, and so this table reports a series of experiments on this same geometry, the barium titanate crystal with a tip, using blue light and varying the intensity and seeing the current increase. And then using AM 1.5, I would draw your attention to this number, the power conversion efficiency for the simulated sunlight, my experimental friends find to be 4.8%, which is 50% higher than the Shockley-Queisser limit for the relevant band gap of barium titanate. And so that's really very exciting news. People have been trying to find photo conversion efficiencies in excess of the Shockley-Queisser limit, but it is rare to actually find this. And of course, the band gap of 3.2 eV is not optimal for collecting energy from the sun, given the solar fluence spectrum. But this is very promising, and it suggests that the next challenge is to find materials that have an appropriate band gap. Okay, so what I've shown so far is that this material lacks inversion symmetry, and so there's a hot carrier effect where the electrons and holes preferentially go one way, and this tip is collecting over a thermalization radius. Okay, so some people think, well, if you're using a tip, maybe you're still collecting over a very wide area, and you're just pulling in carriers from that entire area. So my experimental friends, Jonathan Spanier, did an expansion of this original experiment by Marin Alexei. He used 3 tips, and he got a certain amount of current from tip A, more current when he used tips A and C, and even more current when he used tips A, B, and C together, suggesting that these are each pulling current from separate areas. They're not all pulling current from the entire sample. But I think this is a beautiful demonstration of this. What John Spanier did was he used focus ion beam to mill holes in a silica layer, and then he patterned ITO to make a series of electrodes that are all separated spatially from each other. And this is a top-down TEM view of this array of conductive tips to collect the current. And what happened was that using this array of tips yields many times the one tip current. So if the one tip was really pulling in carriers from a wide area, the 24 tips that are just spaced by a couple hundred nanometers would all share the same current, and you would get no real increase. But an increase by a factor of 5 or 6, something like this, shows that these tips are getting current each from their own little region, and that the thermalization radius that we propose is accurate. Okay, but as I foreshadowed before, the efficiency is great. It's above the Shockley-Queisser limit for an insulating material, but operating up at that high band gap doesn't really make sense. So we really would like to find materials that are polar, so they give us this bulk photovoltaic effect, but have a smaller band gap. And so my students suggested at the chemical level a new way to design materials that would combine polarization and visible light absorption. So we proposed that the perovskite crystal structure offers ferroelectricity. There are many known polar perovskites. But then we suggest using late transition metals because there are many known transition metal oxides that are colorful. And so that is our paradigm, and we began by exploring lead titanate, which is a conventional ferroelectric, with nickel. And so that would give us a reduced band gap. And in fact, we were unable to synthesize this in pure phase form, but it gave our experimental friends some ideas for other pairings of ferroelectrics and late transition metals, and we eventually landed on potassium niobate, which is a well-known ferroelectric, with barium nickel niobate, and this is a photograph of pellets of this material. You can see from their bright green color that they're definitely absorbing light in the visible. And so they carried out a variety of experimental characterizations of this alloy, including applying a voltage and switching them to show that they're ferroelectric, measuring the band gap using spectroscopic ellipsometry to show that they're semiconductors, and then finding photovoltaic current. So this is the first strongly visible light-absorbing ferroelectric photovoltaic, and it was achieved through computational materials design and close collaboration between theory and experiment. It was Peter Davies who did the solid-state chemistry to make this material, and then Jonathan Spanier who did much of the characterization. Okay, and this is a large image of this alloy material, and the idea is that the niobiums have complete octahedral cages, but the nickel ions bind a vacancy, and so their cages look incomplete, and it's this nickel vacancy complex that provides states in the gap to provide visible light absorption. Okay, so but can we go even beyond this and improve our nano-architectonic approach by really understanding where this bulk photovoltaic current is coming from? And the idea in a nutshell is this, that if you have a material with filled states and empty states, if you apply light with photon energy h bar omega, you expect that you can excite from a filled state to an empty state. And in the long term, that's true. But in the short term, you can actually create a coherence. You can create a linear combination of many states, which eventually will evolve to being mostly the energy-conserving state. But for a short time, you create a quantum wave packet. And wave packets have very high velocities and can move a long way in a short time. This is the physical expression for calculating the current due to these quantum wave packets. This is a hot carrier effect, as I mentioned. And it basically is an intensity factor multiplied by every time you have a carrier, how far can that carrier move? Okay, here, transition intensity times what's called shift vector. I would be happy to discuss the physics of this effect with you at a later time. But basically, we use this physical formulation to study particular materials, and this is a comparison between the measured current from experiment in the dashed lines and the calculated current in the solid lines, showing that quantitatively we can predict how much bulk photovoltaic current there will be, and this will work out to what there is experimentally. This result by Steve Young was the first time that bulk photovoltaic current was actually calculated and compared with experiment in this way. Okay, so now that we actually have a quantum theory for bulk photovoltaic effect, we can start to restructure matter to improve the bulk photovoltaic effect. So this is a band structure diagram. That means this is all the empty states labeled by their place in the Bro-1 zone. So gamma is k equals 0, and x and z are edges of the Bro-1 zone, and r is a corner, and so forth. Okay, so we can calculate this shift vector that I mentioned to you. This would be how much current you get. So amazingly, from much of the Bro-1 zone, you get nothing. Do you see it's green? But the interesting places are the red or orange and the blue. So here there is current in the positive direction, and then the orange, there's current in the negative direction. So that's kind of a problem. The fact that we have blue and orange, that means some of the photons will give us current this way, and other photons will give us current the other way. That's going to really cut into our efficiency, isn't it? And so if we have a look, here's what we suggest. If you have the material that we studied on the previous slide, it was this lead titanate with nickel and vacancy, which I already told you about. If you make it as a 1 by 1 by 3 layered material, so you have titanium, titanium, nickel, then you wind up getting a current trace that's the red dashed one. Here, do you see there's negative current and then there's positive current? And that's what we don't like. But amazingly, even though nickel provides the light absorption, just using less nickel and making it a 1 by 1 by 6 So there's 1 nickel, and then 1, 2, 3, 4, 5 titaniums. That gives the purple trace. And there's more current, and it's all the same sign. So this is really just restructuring the material, and there's an electrostatic explanation for this. The nickel-oxygen layer provides a dipole. So you can think of this as a potential drop. Do you see here? And it's the same whether there's 3 or 4 titanium layers. But if there's only 3, you get a large potential drop in the lead titanate part. If it's 4, that's spread out further and it's gentler. The polarizing field is reduced. And this weaker electric field reduces the off-centering and weakens the bonds, which makes the charges more delocalized. And if you have a wave packet effect, you want the electronic states to be more delocalized. And that's a general message that applies to many things. And I could tell you more about that separately as well. But this is a simple example of taking one material and just restructuring it based on an understanding of bulk photovoltaic effect to enhance the current. Okay, so now we've designed other materials with delocalized states. And if you look at the band structure of these materials, do you see there are many states that have pretty flat bands, but the first empty state, look how dispersive it is. Do you see this is something that we like? And it turns out that directly leads to much enhanced bulk photovoltaic current. And this is a graph sort of summarizing bulk photovoltaic currents for many materials. So I told you many of the experimentalists have focused on bismuth ferrite. The bulk photovoltaic current of bismuth ferrite is here in blue. You see, it's from here to here, blue dotted line. Well, and then there's this methylammonium lead iodide that is famous for other reasons. Here is its bulk photovoltaic graph. So it has a lower band gap, but it still has very low current. So look at some of the materials that we've discovered, and I reported to you in this talk. These are the ones that have the dispersive bands. These 3 are the ones I just showed you on the previous slide, blue, green, and red. They have significantly enhanced current compared to the known previous bulk photovoltaic materials. But another material that I didn't really even get a chance to tell you about, we're going beyond oxides. So I mentioned to you that we thought oxides were great for their off-centering polar distortions, but there are polar sulfides and polar selenides, and you know that sulfur and selenium make more delocalized bonds than oxides do. Oxides are more ionic. And it turns out we predict that this lithium arsenic diselenide material, which was recently synthesized by Mercury Kanatsidis, we predict it will have even dramatically greater bulk photovoltaic effect than any of these other materials. 40 times more current per photon than bismuth ferrite. And so with that, I'd like to summarize. I'd like to acknowledge my longtime collaborative friends, Jonathan Spanier and his group. I mentioned his fantastic efforts characterizing many of the materials and their bulk photovoltaic properties. He now has pioneered atomic layer deposition growth of complex oxides, and that's very exciting. Peter Davies has been a long-standing collaborator examining the crystal chemistry of different materials and understanding how to make materials with particular properties in particular phases. And the design of the bulk photovoltaic materials was led by Ilya Greenberg, who's now a professor at Bar-Ilan University. Steve Young formulated the physics of shift current, enabling us to calculate from first principles the current response. Joe Bennett was the one who thought of the late transition metal plus vacancy as a paradigm for new materials. And Vladimir Friedkin is the discoverer of the bulk photovoltaic effect, and it's been a joy to work with him over the last few years. And I'd like to thank these sources of funding, and I'd like to thank you for your attention, and I welcome your questions.